Fine. So, good morning, everyone. We will start the session today. Uh, I don't like taking week 5 session now. You know why? Because none of you are interested about week 5. Because you guys have quiz and all, so no one is interested. Anyways, so honestly, tell me how many of you have gone through the content. I see. I'm not expecting you, but at least if someone has gone through, raise your hand. And if don't lie, only 1%, 2%. Okay. Great. Very sincere people. So, in the last session, we have discussed, I think, um, lossless decomposition and your functional dependency, idea of functional dependency, lossless decomposition, and yeah, candidate keys and stuffs like that. So in this session, primarily we will discuss and see in the lecture, sir has discussed a little bit of BCNF and stuff. If you guys are having difficulty in understanding that, don't get worried. Okay, so we will do the normalization related topics. So 1NF is done, I think, properly, but 2NF, 3NF, BCNF, 4NF. So all these normal forms and all these normalization related topic we will do in much detail in the next week. Okay, so don't get worried if you do not understand. So I mean anything regarding BCNF, if you do not understand, you will we will discuss that in detail later on. Okay, I mean without going through the steps of 3NF, 2NF, it is little bit difficult to make you guys understand what BCNF is. But due to the, let's say, I mean, sir has discussed it in a in a particular style in the lectures where the BCNF, I mean, shortly it is discussed. So if you are having difficulty in that part, don't get worried. We will do that in a sequential manner later in the next week. Anyway, so but this week is very important for you guys to understand normalization because we will deal with stuffs like this the canonical cover, functional dependency. If you do not understand these things properly, you should more properly say that if you do not practice these things properly, then you will not be able to do normalization related question. And normalization, there will be many normalization related question in your quizzes, right? And in term also. So normalization is one of the most important topic of database management system, a relational database management system. So be careful about it. Another thing I would request you guys regarding your upcoming quiz, please go through that ER diagram session, right? Both mine and as well as I think the next ER diagram session was taken by Piyush, I think. Yeah. So please go through those things. It's very essential. You want to say something? I think someone unmuted. You wanted to say something? Okay, sure. So, yeah, okay, go ahead, go ahead. Someone wants to say something. I think.
Which diagram session? I did not understand which
Year
session.
diagram, year diagram. So the week 4 session, right? I think, yeah, week 4 session. So go through the week 4 live sessions properly because where you have to draw the ER diagram, what is entity, what is relationship, how you do that. So go through that properly because questions will be there from that part because that's where you basically design the database according to the constraints given, right? Okay. So before moving into a new topic like dependency preservation or canonical cover, let us have a, I will ask you guys a few fundamental questions. This in the screen. So in the lectures we have seen this. Yeah, here is that functional dependency. I'm not going through the basic ideas. I think these things are discussed. Why we go for this? The what is lossy decomposition? What is all those things? Right? I hope those things are clear to everyone. what I want to ask you guys is, what is that function? Yeah, functional dependency. So let's take this as an example. Right? Here we have this table given to us, and we have accordingly some functional dependencies. And in the multiple problems also, which you guys must have seen in the last live session, that we were basically solving many functional dependency related questions, A, B, C, D, whatever. So what are those A, B, C, D? Do not get confused. These A, B, C, Ds are basically alias of these kind of real life attribute or column name. Okay, so student ID. Every time writing student ID, semester, lecture, I mean, this is difficult. That's why we use these aliases A, B, C, D. But idea is same. I mean, some students even do not understand that, and they think that what is that ABCD and what are these table column names. So they are same thing. Or if anyone has doubt in that, no, don't worry. Basically, they are the same thing. We use those aliases because it is difficult to write the full column name every time while solving normalization problem. But that is fine. What a more fundamental question that I wanted to ask is, so what do we do? We basically derive this functional dependency. So let's say a table is given to you, and we see that whether a particular functional dependency is holding or not by seeing the data of the table. So let's say in this particular given table, I see that student ID 1234 is in row number 1 and in row number 3, right? So here student ID is 1234. Here also student ID is 1234, and semester is 6 accordingly. Lectures are different, the two different subjects that that student is taking, and the TAs are different. Okay, so that is perfectly fine data. So that means student ID determines semester. So if you know the student ID, obviously that same person will, since this is the same person, his semester will be same. That's why you have this student ID determining semester. So we derive this from the table, and then once we have derived this set of functional dependency, then we go on solving them. What I want to ask is, do you think there is some problem, not with respect to this DBMS and forget about those things? What is the fundamental issue in this kind of approach? We are seeing the table and then determining the functional dependency. Any idea? Think in terms of normal, practical, real life situation. You do not have to think in terms of DBMS and this technical study related stuff. What is the problem with this? I am deriving functional dependency on the basis of table data. That's what we have been doing, right? So yeah, any idea, any thoughts on this?
Duplication of data.
Duplication of data, how? What I'm saying is, I hope my question is clear, right? What I'm saying is, so let's say student ID determines semester. This is one functional dependency. Now, how we are getting this functional dependency? Because we are seeing the table given to us. That's what we have done in the last session also, right? And the lectures also. That this table is given, on the basis of that we are deriving some functional dependency, and then we are working, finding candidate key, whatever. So we will do some task today also. But what is the problem with defining the functional dependency on the basis of table data?
If there is a large set of data, it is not possible to view the table and derive the functional dependency based on that.
Correct, right? If the data is large, then it might so happen that maybe in the first few entries you see that, okay, these are the trends that is holding, but later on maybe that trend is not holding. Maybe that is violated. So if even a one violation of property is there, so then that will no longer serve as the proper functional dependency. So how does it happen in real life? I mean, solving these multiple theoretical questions is fine, but when you go to industry, or let's say you work upon a project, how does this thing really work? What is the real life situation? How will you deal? So basically, you want to you want to set up a database on some project, right? So how will you first encounter this functional dependency subtopic? Any thoughts on that?
Sir, mostly the domain expert will decide upon those FDE rules, and based on that, we'll perform further tasks.
Correct. So can I reword your answer and say that the table data doesn't determine the functional dependency. The functional dependency is decided at first. On the basis of that, the tables are populated. Can we say that?
Yes.
It is actually that only. Okay. So see, for solving questions and for understanding the topic, in all lectures, what you will see the approach is you are introduced with the topic of functional dependency by showing you guys a table data, and then we see that okay, student ID 1234 is repeated twice in row number 1 and row number 3. So whatever attribute who has values same, whenever the student ID is same. So if the student ID agrees between two rows, then if some other attribute 2 agrees on those rows, then I say that student ID determines that particular attribute. And that's why we say that student ID functionally determines that attribute. So this is the basic introduction of functional dependency. But the thing is, in reality, it's not like that. In reality, you will not have the table. You will not even have the database. This functional dependency will be decided as business rules by the guys who is your client, right? So you are the technical guy, you are making the database, and some people will be there who have given you the job to do. Let's say your company is working with a bank, that bank has given some rules that these are the requirements that I need to have, right? So on the basis of that, on the basis of business logic, some constraints will be found, and on the basis of those constraints, we derive the functional dependencies, right? So once the functional dependencies are derived, according to that we fill up the tables later on. According to that, the data are inserted, right? So this is something which is very important. So this is a part of database architecture. So where you are the architect of the database system, and you define which table will store what are the constraints between different rows and columns, right? So that part is basically that deals with this thing. So if you have heard the data engineer profile, those guys, and data engineer profile is a little bit different, but many of those guys also work in this domain, but database architect particularly work in this domain. So be clear about this fundamental idea. Functional dependencies are not derived from table. Functional dependencies are business logic, as one of you said, that it is given by the domain experts, or let's say in real situation, it will be given by your client. Basically, with the meeting, when your company goes and meets, they will decide that these are the rules. And once that is done, then you define these multiple attributes. The database architect will determine the multiple attributes, and on the basis of those business rules, he will set constraint between these attributes. And these constraints are nothing but the functional dependencies. Now, on the basis of that, data will be populated within your table. Now, once these things are done, once the tables are populated, then you see that there are some troubles, and that troubles are basically because of redundancy. And those things are discussed, I think, in the last session, that when you have redundancy in the table, when you have multiple copies of data stored at different places within the same table, then you run into some problems, basically because you have duplicated entries. If you change one entry, the other entry might not get changed. For the same data, you have 2 and more updated entries which are not matching with each other. So these kind of anomalies may occur, and due to the redundancy, this is occurring. And because of that, what we do is we try to separate the tables depending upon specific rules, and those rules are actually your lossless decomposition rule, and that is done on the basis of functional dependencies. Right. So this is I think this is the progression of how things actually goes in real life when you work with databases. Now, once you have separated the tables and done the things, then you come to the idea of normalization. That okay, normalization, again, this is nothing but normalization is again a more formal way of or a set of procedure which you can follow to eliminate redundancy in a much better way. Right. So first normal form will have less redundancy than an unnormalized database. Second normal form will have much lesser. Third normal form again will have much lesser redundancy. Likewise, and BCNF will have no redundancy, so to say. So not no redundancy, but yeah, mostly it is very desired state of database. So this is the whole idea of the database normalization. And in order to do that, we need to learn some tools like finding candidate key and all those stuff. And we will learn 2 more tools today also, which is particularly dependency preservation and canonical cover. Right. So before going into that, let me now ask this: you guys have any doubt till now what we have done, or what I discussed today, or in the previous session, whatever was discussed? Don't raise hand. Okay, please tell. Again, I'm just saying because I will not see who is asking.
Okay, my question is, you mean to say that the management is first decide the rules,
Correct.
means what is the key and what thing is depend on the key, and after
Not
that they
only,
will insert
see,
according.
just a second. So non-key attributes might also have functional dependency, right? So
Okay, okay.
in this case, there is no such example, but let me go to another table. Maybe we will, yes, is this department ID. So department ID is not a key over here. Employee ID is a key. I mean, if you see this table only, right? If you make a separate department table, that is a separate story. But in this table, department ID is not a key. Yeah, it's not a key because it is getting repeated. Yeah, so it is not a key, but it is still defined functionality defining department name, right? So these are the rules. These are it's not always that a key will be a part of functional dependency. Non-key attributes are also functional dependency.
Okay, okay. You mean to say that they will first this define rule,
Correct.
then they will insert the data, and let's say I have the inserted employee ID first. Okay, and
Okay.
then I will use again this ID, and the employee name will be automatically so.
Not you have to enter the data, right? I mean, if the constraint is violated, so let's say, I mean, if you have the employee ID as already you have set it as a key, and you are mentioning that employee ID twice, then your employee name must be same. That constraint is there. So if you have set the table according to that constraint, whenever you enter something else, so let's say employee ID 0001 is repeated twice in real life when you are making the table, it repeated twice, and you have already set the constants like employee ID determines employee name. So later on, when you are populating the data in the second row where employee ID is repeated, if you enter a name other than John Doe, something else you enter, then the database engine might raise an exception that this is an error. Why you are entering some other values, right?
Okay,
So that will happen.
okay, understand.
Got the
Thank
point? Yeah. So the idea is in real life these are business logic, and because of this business logic, we set the table according to that, and the data is populated within the table according to that. Later on, after all these things are done, after the business logic is decided on the basis of that, the table attributes are decided. How many tables will be there, that is decided, because we saw the ER diagram, right? So we have done the ER diagram part. So at first the ER diagram will be made. Along with the ER diagram, so ER diagram is used to convert the ideas of the database given by the client into real life tables, right? Database table, we have seen that. So once the ER diagram is made, engineers will convert that into table, right? Database tables. So once the database tables are made, then the question comes, okay, now I have the attribute names and all those things, right? So now I have to check what are the other business constraints that have been given to me. So those business constraints are basically these functional dependencies. Now, once that is again given, and that is according to that, we fill up the data into the table, populate the data into the table. After that, you see that, okay, these are the problems, these are the places where redundancy is occurring. So we need to do something about it. So then we do the normalization stuff, and we separate the tables according to the rules of normalization, according to lossless decomposition, all those things. So this is the what should I say? This is the path. This is the way things proceed sequential. Anyone else? Any doubt in this?
What do you mean by normalization?
Normalization primarily we will discuss in the next week, but normalization is again, as we know that why are we doing all this? To reduce redundancy, right? If there are multiple entries in the table, then we will get into anomalies as discussed in the last session. So to reduce redundancy, we will do some task, and that task is basically normalization. Essentially, normalization is following different rules to break a big table into smaller tables. Okay, simply stating in normal English, you are having a big table, you are separating that big table into smaller tables, but you are following some rules, and those rules are normalization rules. So once you follow those rules while breaking the big table into smaller tables, these smaller tables will have much less redundancy and will be lossless decomposition. So basically, your complete data set will be preserved, all the meanings and semantics will be preserved, but you will have no redundancy. Not no, I mean, very less redundancy or no redundancy. If you go higher in the forms of normal forms, you will have no redundancy left. That's the idea. Okay, and we will discuss that in the next week. How normalization is done. Okay, I think everyone is fine with it. Right, so let's go to the discussion, today's discussion, which is lossless decomposition was done. I think functional dependency preservation and canonical cover. So let us do the canonical cover at first, then we will do functional dependency preservation. I think 5.4. Set closure is discussed. Cover, canonical cover. So what is a canonical cover? A canonical cover is nothing but a minimal set of given a set of functional dependency. You might have many redundant functional dependency in that, right? So basically, some functional dependency might be given in that set of functional dependency, which is not required. I mean, one functional dependency implicitly derives the other one, and you have given both of them as a part of the FD set, functional dependency set. So one of them is not required. It's redundant, right? So you are mentioning the same thing twice indirectly. So that's why. So let's say A goes to B, B goes to C, and I am also giving A goes to C. So it's not required to give A goes to C, because if we are giving A goes to B and goes to means this arrow, okay? So A goes to B and B goes to C is there, then that essentially means that if I use the transitive logic, then A goes to B, A determines B, B determines C. That means indirectly A determines C. So you don't have to explicitly mention A determines C as a part of this set, right? Functional dependency set. So that's why A determines C is a redundant FD in this set. So simply these are the, so if there is a redundant functional dependency in the set, we will not say it is minimal. Only when there are no redundant functional dependency, and whatever functional dependency is left over in the set, they are unique in their own capacity. That is, if you remove any one of them, the functional dependency set's idea will get changed. The whole, I mean, whatever it was doing, the meaning will get changed, right? So if all the functional dependencies are important to be given as a part of the FD set, then such a set, such a functional dependency set is called minimal or irreducible set of functional dependency. Okay, now that is what basically is minimal. I mean, given whatever functional dependency set was given to you earlier, you reduce the redundant, I mean, you eliminate the redundant functional dependencies and you get a more, let's say, concentrated set of functional dependencies, provided that the meaning is not lost. So whatever was achievable or whatever was definable in the earlier functional dependency set, after reducing the redundant ones also, you are not, let's say, compromising with the defining capability of the FD set. Okay, so whatever was done by the earlier set, now also you can do, but with lesser number of FD. So if you, this is what we call covering. So you can cover the same amount of determination, functional dependency determination, by the reduced set as well, just like the original set. Okay, so that's why we call it cover set. So what is the way to do that? So I give you a functional dependency set and ask you to find the minimal cover or canonical cover of this set. So there is a, I mean, there are steps to do that, and we will see that. Let's take an example from here. For example, on LHS, let us take something more. Okay, so let me take one example from, these are little bit simple ones. So we will take, okay. I hope the white screen is visible, right?
Yes, sir.
Yes.
Yes, sir.
By the way, can someone say why is this canonical cover important? I hope you guys understood what canonical cover is. Is there any doubt in the canonical cover understanding what it is?
So we want to reduce the number of FDs as much as possible.
Correct. Without actually compromising with the meaning of the FD, right?
Yes, sir.
So what is how is it beneficial? Reducing, I understand. Anything you reduce, that is good. But how is it actually beneficial?
We can understand the dependency within the less amount of equations like
Correct.
A dependent B.
Correct. So when you are basically defining these functional dependencies, right, you have to follow these rules while populating your table, right? And basically how it is done is you will set multiple triggers. I hope you guys have seen triggers, basic discussion. Yeah, so triggers and some other assertions are set in real life database designing. So where they put these constraints to to execution by setting triggers and assertions. So if you are entering a data which is not according to the rules, then it will raise an error or raise a warning that this is not the proper insertion, please, because it does not follow the business logic. So please enter the data after making the correction. So this kind of prompt will be given, and that insertion will be that insertion will be reverted, right? So if you have multiple dependencies, lots of dependency, and there are redundancy within them, so unnecessarily we are putting pressure on the system by putting redundant constraints, which will anyway hold by using lesser number of functional dependency constraints, right? So if we are unnecessarily putting multiple code, this code means the code used for putting constraints on the table. So you will unnecessarily write multiple codes, and that will put more load on the system, more checking on the system, because each constraint checking takes time, right? So if you put a E, let's say here A determines C. So if I put a constraint like that on the table while populating the data, and it is automatically, don't think people check the A and C attribute and feel accordingly. It is done automatically by setting up an assertion or trigger. If you put something which is not according to the A function determines C constraint, then it will raise a warning or error. So this is automatically done. So automatically done means the system is doing that check whenever you are inserting something into the table, right? So if you have you have configured multiple such checking mechanisms, right, then it will be difficult for the system to do that. I mean, unnecessarily you are putting load on the system. So that's why we reduce it. So there is one thing I would request all of you guys to try to do it in your study. This is not with respect to DBMS or anything. Always try to relate your theory. I mean, this might seem a very redundant kind of advice. You might have heard it many times. But I'm saying this because it is very difficult to relate the theory part with real practical part when you are working. You might have learned the theory, but when you are doing the practical, we do it in a way that we do not recognize that this is the theory that we have already learned. I mean, you do it in a different kind of way, and that's why most of the time we are not able to relate it. Okay, so be careful while doing your practical. If you can relate these two things together, then it will be very much beneficial for you guys. Okay, so let's say this is the functional dependency set, FD set, that has been given to us. Okay, and what I want to do is I want to reduce it. First of all, let us see whether it is reducible or not. That is also there. So please pay attention. There are a few steps that we will follow in order to find the canonical cover or minimal cover, whatever you want to say. So the step one is, first step is you separate the right hand part attributes one by one. So I will make the functional dependencies. So step one is separate RHS attributes. So what do we mean by that? What we are basically saying is we will make the set as A goes to C. So right hand side only one attribute is there. Okay, so fine. Left hand side I'm not worried, right? AC is 2 attributes, but I'm not worried about that. Right hand side only 1 attribute is there. It is also fine. Now here E goes to AD has 2 attributes. Here I will separate it into 2 parts. Fine. So step 1 is done. What is step 2? Check for redundancy. So this is most probably the most important step. So how will we do it? So see, the way we will do this is we will take, so from left hand side start. So this is the A determines C is the first functional dependency, right? So we will take this we will take this dependency and see whether it is possible to get this dependency using the other dependencies that we have. Got the point? So just think that this A determines C is not there. Whatever else is there, right? Whatever else, so all these dependencies that we have over here, we will use these dependencies to derive A determines C. If I can use these dependencies to get to or to derive A determines C, then basically A determines C is redundant. So I don't need it. So let us, can anyone tell me whether is it possible to determine A determines C from this?
No, sir.
No.
Sir.
No, right? We cannot do that because C on the right hand side, none of these dependencies C is not there on the right hand side. So you don't have to worry about anything. It is not possible. So A determines C is necessarily one of the required dependency. So now let's move to the next step, which is this dependency. So now A determines C is compulsorily there. So I will use all these 3 things, 3 dependency and A determines C, to check whether AC determines C can be derived or not. So is it derivable?
Yes, sir, we can derive.
Okay. So let us see that A determines C is there.
Sir, not entirely, but
Think about it. So let us see what happens. So AC determines C. D. This is what we have to find. So we have A determines C. If I have AC, right? How we will do it is, if this is the dependency that I have to derive, I will see what is on the left hand side. So AC. Now consider this dependency and these dependencies are there with you, right? These 3 and this dependency is there with you. And what is in your hand? You have AC in your hand. Now tell me whether by using these dependencies and this one, these 4 dependencies, and with starting point being AC, because the left hand side is AC. Starting point being AC. So you already have A and C. And then by using these 4 dependency, can you derive D or not?
sir, if we use the Armstrong's axiom, then only it's possible.
How?
So we'll use augmentation then.
Tell me, so how will you do that?
So we know that A determines C.
Okay.
So we can say
You cannot use this one. This is the one which you are trying to prove redundant. So forget about it. So
we can say now I think AD is equal to CD.
So let us do it in this way. So let me just tell this again. So what are we trying to do? We are trying to check redundancy of AC determines D. So that means I will use the leftover functional dependencies which I have. What are the leftover dependencies? 4 dependencies. Now, what is in my hand? Since I want to check this dependency, I will start from the left hand side, which is AC. So I have these 4 dependencies in my hand and I have AC. Starting point is AC. Now let us say AC. So what is AC? So these things you know, right? Attribute set, AC plus. So what will be AC plus using these 4 dependencies? Tell me.
It's only AC.
AC will be there. Other than that?
Nothing.
Nothing, right?
Yes.
Yeah. So that's it. So since it's not there, only you can have AC, right, as the attribute set. By using these 4 dependencies and starting with AC as the starting point, we are not able to find any D, right? So that's why this dependency AC goes to D is also important.
Sir, but in AC determines D, we can see that C is extraneous on the left
That
hand.
is something we will do later. Okay, that is next step. Okay. First, you have to check redundancy. So we will move step by step. Okay. So this is also done. Now the third one is E goes to A. Is it definable with the other dependencies that we have?
No, sir.
No.
Because
sir.
A is not on RHS apart from that.
Next one.
Yes, sir. It can be derived. E gives D can be derived without using E gives D. We can say E gives A
Correct.
gives C, and AC gives D.
So E will take A using this. So E will give A. Now A will give C using the first dependency, and the AC will give D. Right? So basically E will give D. So E goes to D is definable using the other ones. So I will not write E goes to D as a part of this reduced set. E goes to H, yeah, it is again required because H is not there in any other dependency, so no need to check anything else. So now this is your reduced set. Okay, so this is your reduced set of dependencies. Now,
I did not understand that part. AC goes to D because we have A closer set. In that we got A and C. After that we can go to D, AC to D.
how? Let us see that.
Yeah.
AC
A
goes
closer
to
set.
is the dependency under consideration. So I will black box it. I will not see. I mean, forget about this dependency. I have AC with me, right? AC plus, and I want to find out the attribute set of AC plus using the other four dependency. Now tell me the attribute set of AC plus using the other four dependencies.
D.
How? Where are you getting these? These are the dependencies which you have. These four, right? 1, 2, 3, 4. Now tell me. With starting from AC.
Can you make the A closer set?
Yeah, that's A closer set. Okay. If I have A closer set, I will have A, I will have C.
Then we
And
have A and C, then we can go to the D.
D is the one you are considering, man. This is, you cannot see this function dependency. You are
Oh,
checking.
means you will be apart this set, and you, if you can derive this without this set, then it will be
That's the
redundant.
meaning of redundancy, right? If you are considering that, then what is the meaning? I mean,
Okay, 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 understand.
right? Fine. So this is done. Now next step is check for redundant functional dependencies are done. Now we will check extraneous attribute, as I think someone was already pointing out. So what is extraneous attribute? Now this is something which deals with the left hand side LHS part only. So this was but RHS part only step, the first step, and the last step is LHS part only step. So here I will see whatever in LHS side I have multiple attributes. In whichever dependency I have multiple attributes, I will see whether I can derive any one or more than one of the attributes using the other ones on the left hand side. So if I have let's say A, B, C, D, whatever arrow, some values, right? So I will see that whether I have extraneous attributes over here. So what I mean is, let's say AC determines D, one functional dependency is there. Oh, by the way, it is there also. Right? So AC determines D, functional dependency is there. So that means I have AC together, then writing D is extraneous, redundant, right? If I have AC, then automatically I will have D. So you don't need to write D as a part of functional dependency. This is repetition of information. So I will remove this D from here. Okay. So this is the basic idea. So I will have ABC. So that is called extraneous attribute removal. So we will do that in this step. Obviously, you can understand according to the logic that this is only possible when you have composite attributes on the left hand side, and in all of this you have only this dependency where composite attribute is there. And obviously I can see from the first dependency that A and C are basically redundant, because if you have A, then you can determine C. So mentioning AC together is, redundant. You don't need this. So therefore AC goes to D is reduced to A goes to D. That is enough. And everything else is anyway atomic values. So this is my new set, and you can now just compose it together as A goes to CD and E goes to AH. So this is basically your canonical cover. Now, why do we call it cover? Now do an exercise and see that whether the first functional dependency which we had, basically this one, functional dependency set, all of those functional dependencies can be, you can derive them using this small set only. So let us try that. The first one was A goes to C, right? So obviously A goes to C is there, okay. Then AC goes to D. So how can we derive AC goes to D? So basically what we need to find is AC closure. What will be AC closure? According to this one, applying on, let's say this is F dash. So AC closure on F dash. What will be it?
ACD.
ACD. Right? So ACD means AC can determine D. So this functional dependency is also undercover. Right? So then we have E goes to A. So what is E plus on F dash on this new set? If I do E plus, then E goes to E, A, H, C, right? D, all of them, C, D, right? So it's because E goes to A and H and A goes to C, D. So E, A, H, C, D will be E plus. So E goes to A, determined, done. E goes to D, done. E goes to H, done. Okay. So you see that we have all the dependencies given to us being covered in the F dash, and we have only 2 dependencies in the last one, whereas we had 4 dependencies in the first dependency set. So how many of you have doubt in this process? Any doubt? Think about it, go through. I will wait for 1 minute. Read it, go through it, try to solve it in your brain once again, and then we will proceed with the next example.
My doubt is AC closure set and A closure set exactly same, right? ACD.
Correct.
Sir, in the last step, E determines AH. We can do this in the last step only and can't do it in any of the previous steps.
You can do it, but you will run into trouble if you do it in the middle. Why I am saying this? So let's say in step 2 you join E and H together, right? So actually not in step 2 also. Let's say in the first step only you kept it as a composite value E H together. Then while going for step 2, when you are checking for redundant functional dependency, you will feel difficulty. Now this example might be a moderate level example or easy level example. If I give you a tricky example, and if you join the right hand sides together in the first or let's say in the second step only, Then while checking for redundancy behavior, you will feel difficulty. I mean, there is a chance of doing some mistake. That's why we separate the right hand side into single attributes. You can do that if you are, I mean, if you can find out things, then you can do that. There is no rule that it has to be done in the last step, but it is done so as to not confuse ourselves and make mistakes.
Okay, sir.
Excuse me, sir.
Yeah.
So why are we considering AC closure and not A closure?
AC closure. Oh no, that is because I am trying to figure out, I mean, I am trying to recheck that whether all the dependencies that are given to me in the primary parent set, whether all of them are covered or not. Okay, so since the first one was A goes to C, then I will check A plus. And I got A plus as, I mean, you understood, right? So basically each of the functional dependency we will pick up, and I am checking whether the new F dash set covers all this dependency or not. So in order to check that, what we will do, we will take each of the dependency, take the left hand side, or in the primary set, right? We will pick each dependency from the primary set, which was given to us in the question. From that, we will pick the left hand side, all the left hand side values, right? We will pick all of them one by one, and we will find the closure of them in the new set, which we derived. And if we can find the corresponding RHS in each of these closure set, then we can say that, yeah, our all the functional dependency are covered. So here I have done AC plus because the second dependency was AC on the left hand side. So I wanted to check that if I find AC closure set on the F dash, what am I getting? Right? So we are getting ACD. So that means AC can determine D. Actually, A itself can determine D, but here we are trying to check this left hand side is holding or not. So that's why we did it. Is it understandable? Is it okay? Or you have any doubt? You did not get it? Okay. So the simple thing, we are not doing anything new over here. Once we have derived this dependency set, we are basically checking whether all the dependencies given in the parent set is holding or not. Now, in order to do that checking, what we have to do? We need to check that the left hand side is determining right hand side or not. So AC is determining D or not, E is determining A or not, E is determining D or not, likewise all of them, right? Now, in order to check that, what are we doing? We will take the left hand side and we will find the closure of that in our new functional dependency set. And if in that closure set, I get the right hand side of this particular dependencies, right? Right hand, if I get the right hand sides of the parent dependency set, then I can be sure that my derived dependency set covers all the functional dependencies of the parent dependency set. I am not losing any information. So that's why we did AC plus over here, because we are trying to check whether this dependency is lost or this is preserved. I mean, can I derive this AC determines D? So that's why we did AC plus. Okay. If anyone has any other doubt, we can go solve that. Otherwise, we will proceed with the next example. Fine. So let us solve one more example of this canonical cover. Whatever. Is my cursor visible on the screen?
Yes, sir.
Okay. Fine. So let's say this one. One question from canonical cover will be there, compulsorily will be there in your quiz. Not one, I think, yeah, more than one, because one question might be simple cover, another might be canonical cover. So what do you mean by simple cover? Yeah, did you get what I mean is, let's say two sets of functional dependency are given. So let's say FD1 a set of functional dependencies, right? Multiple dependencies are given. FD2 or let's say FD2, FD1, two sets, right? Again, another set of functional dependencies will be given, and we are asking you that whether FD2 covers FD1 or FD1 covers FD2 or both of them covers each other. So something like that. So how to solve those kind of question? So let's say if I want to check FD1 is covering FD2 or not. So just the thing that we did over here, right? What did we do over here? We checked that f dash is covering this initial functional dependency set or not. And the way to do that is you check the left hand side and find the closure set in the new functional dependency which you are checking for cover or not. Right. So likewise, if I let's say ask you in this, we will take one example later on. Let us not get confused, but I'm just saying. So let's say FD1 and FD2 are there, and I'm asking you whether FD1 covers FD2 or not. Whether FD1 covers FD2. So that means all the dependencies in FD2 must be covered or must be derivable by using FD1 itself. So the way to check that, so this is question. So the way to check that is you pick each dependency of FD2, right? Whatever dependencies are here, you pick each one of them, take the left hand side of each of them and find the attribute, same thing, same attribute closure in this new FD1. Because I'm checking for whether FD1 is covering FD2 or not. So I will take the left hand side of all the functional dependency in FD2 and find their attribute closure in FD1. In FD1, okay, not attribute closure in FD2. That is meaningless. In FD1, I will find their attribute closure. And if I see that in the closure, the corresponding right hand sides are there, then that would mean that I have FD1 covers FD2. Okay. We'll see one example later on. Okay, so AD goes to E, E goes to C. Yeah, so tell me. Let us solve this. Step 1 is what? Separating out. Oh, all of them are same anyway. One attribute only. Okay, what is step 2? Checking for redundancy. So AB determines C. Let us find AB plus in these three. Right? So what is AB plus in these three? A, B, E, C. That's it, right? A, B, E, C. Correct. So if I have this A, B, E, C over here, then AB determines C. I can have this AB determines C over here. So that means AB determines C is something that we don't need. Did you get it?
Yes, sir, it's redundant.
Yeah. So AB determines C is not required. Next is D determines C. So let us find, so AB determines C is out. Okay. So anyway, I have these three dependencies now. So and now I want to check whether D determines C or not. So when I'm checking for D determines C or not, I will only use these two, the other two. Right? So nothing, because we don't have D. So anyways, we need D determines C. So D determines E will be needed. Now let's say AB determines E. So again, I have the other two dependencies, these two dependencies, this one and this one. So let us check AB determines E or AB. Obviously, we don't have AB. So anyway, we need to have this, right? So basically, we are finding AB plus again. In what? In these two, in this one and this one. And so anyway, we will not get anything other than AB. So that's why we need to have AB determines E. And now E determines C. So again, C is not there in the other two. So E determines C is also necessary. So step 2 is done. What is step 3? Extraneous attribute. Only one example is there of composite. So A determines B is there? No. B determines A is there? No. So no AB is there. So basically this is your reduced form. Okay. Got it? Any doubt? This is rather simpler example than the other one. Okay. So as I was telling you guys that we will do one cover question, that whether two given functional dependencies cover each other or not. So let us take this example. Let's say F is a functional dependency set. A determines C. AC determines T. I think this question came in GATE once. Hey, is this the one we solved earlier? Okay. So this is really, anyway, we have solved it anyways. So we will take another example. Let's take this one, A, B, B, C, C, D. Right, now I'm asking you that whether F covers G, G covers F, or both cover. So there are three doubts and I need to check that. How we will do it? So let us do the first one. So let us take step first one, which is basically F covers G. This part. So when I am checking whether F is covering G or not, how to do it? So we will take each, since G is the one which is under check. So I want to have F, all the dependencies of F serve all the dependencies of G. So whatever dependencies are there in G should be derivable by using the dependencies of F. I'm saying it once again. Whatever dependencies are there in G, I mean all these dependencies, must be derivable by using the dependencies of F. Then I can say that F is covering G. How to check that? So let's take the first one. A goes to BC. So what I have, left hand side A. So I will apply what? A plus or A closure set, attribute set on what? A attribute set on F. Right? So what is A's attribute set on F?
A, B, C, D.
Okay. So A's attribute set on F is A, B, C, D. So if that is so, what is happening in G? A goes to B and A goes to C. So obviously here also I am getting A goes to B and A goes to C. Right? So therefore this functional dependency is holding. Now let's take the other one. Here C goes to D is there. So I will find what? Left hand side is C. I will find C plus. Again on F.
CD.
C comma D.
Right. So again this is C comma, here D was there. Here also I got D. So both of these are holding. Fine, great. So I can say that yes, F covers G. Now let's take the other part. G covers F. Okay, same thing, but from the other way around, what we will do first is A goes to first is A, this one, right? We will consider from this one. So A goes to B. So left hand side of that is A plus on G. What is A plus on G?
A, B, C, D.
Right. So here I have A goes to B, and here also I have A goes to B. So first one is holding. Let's do the second one, B goes to C. What is B goes to?
Nothing.
Only B, right? And
Yes, sir.
trivially B will be there. Other than that, we do not have anything. So that means what? Here I have B goes to C, but here I do not have anything. I could not derive C using the functional dependencies of G, right? So that means this functional dependency of F is not derivable by using the dependencies of G. So that means although F covers G, but G does not cover F. Got it? Now think about it. Again, I will wait for 1 minute. Understand this properly. In all of these kind of, I mean, whatever we are discussing, 1 or 2 questions will come in each of these examples. Go through it, I'm waiting, and if you have doubt, ask.
Sir, in the previous example,
Go ahead, one by one.
Sir, can you explain it once again, sir?
Okay, and someone else was asking in the previous example.
sir,
Complete it.
my doubt was that in the previous example, the canonical cover we got was D determines E, AB determines E, and E determines C. So can't we simplify it further by writing AB, D determines E? And
Wait. What are you saying? So this was the question, right? Okay. Now which
yes,
one
sir.
was the? Yeah. Tell me what are you saying?
So can't we further simplify it by writing A, B, D determines E, and then further E determines C?
A, B, D determines E, and then say E determines C. Yeah. So the thing is, you are basically merging these two functional dependencies. Now the
Yes.
thing is, when you are writing A, B, D determines E. So let's good question. Nice, interesting point. So let us see this. I will come back to that cover question later. Just let me address this first. A, let me take another color. Monotonous हो गया. अरे यार. Let's take this one. So what we are trying to do over here is, I have A, B, D determining E and E determining C as the functional dependency set, right? And the other one was D determines C, AB determines E, E determines C. So E determines C, तो ठीक है दोनों में, just leave it. But other than that, we have this part. Okay. Now, whenever we are writing A, B, D determines E, forget about this FD. Okay, so forget about this functional dependency set. Just assume that you have only this set. Okay, don't see this part. Don't see this whole thing. Forget about it. Just see that this is the functional dependency. Okay, now if I ask you in this particular functional dependency, can I derive E without D? So what I mean is, what would be AB plus in this set?
So ABEC.
ABC? How? AB is there, then
Only AB.
you got my question, right? So can you please tell your name, because you are asking this question? I want to know.
Sir, Devangi Roy.
Okay, Devangi. So Devangi, what I mean is, just see this dependency set. Okay, forget about everything else. This is a new question, let us say, and this is the new FD that has been given to you. Now tell me what will be AB plus in this new functional dependency set. So you have AB, so A and B will be trivially there. But can you derive E without D? So in this set we have the functional dependency A, B, D together deriving E. Unless and until I have D with me, so here I do not have D, right? I'm trying to find AB plus. So unless and until I have D with me, I cannot derive E. Right? Because then that would mean if I could have written E in this place, then that would mean that AB goes to E is a functional dependency. Right? But that is not there. Here you cannot see that.
Yes, sir. Okay, sir. Thank you, sir.
Got the point? Okay.
Yes, sir.
Yeah, so I think someone was telling something in the between. Go ahead and then I will come back to the previous question. Solve it once again. I think someone was telling something. Any inputs on this? No inputs. Fine. Okay, so this is actually covering is not that difficult. What I mean is whenever we are trying to cover one empty set with another, if I check, so let's say I will briefly tell once again because we have discussed it. So F covers G or not. So F covers G or not. So when I'm checking for whether G is the one which is covered or not, I will take the functional dependencies of G, take their left hand side and find their attribute set closure in the one which I'm checking for coverness, right? So which is F. So I will take G's each functional dependency, pick up their left hand side. So in this case, I will pick up A and pick up C and find their attribute set closure on F. That's what I'm doing. Here A and C's closures are calculated. And on F, I get the closure set as ABCD. Here I got the closure set as CD. Now, if I see that in this closure set, I have the right hand side of the G's functional dependency, right? So I took A and G's functional dependency was right hand side BC. So in this closure set, do I have BC? Yeah, I have B and C. So that means this functional dependency is covered by F, by the F functional dependency set. Accordingly, for C and D, right hand side was D. So in C's closure set, do I have D? Yeah, I have D. So that means this functional dependency is also covered by the F set of functional dependencies. So I write yes, F covers G. But on the other way, when we are trying to find the same thing for G covers F or not, now I will have to take each functional dependency of F, take their left hand side of each functional dependency of F. I will take their left hand side and I will check the closure, attribute set closure of each of those left hand side on G, this time on G, because G is the one which is trying to cover F. So if I take, so first dependency is what? A goes to B. So I will take the left hand side A and check the closure of A on G. So what is closure of A on G? Closure of A on G, that's why you see closure of A on G is A, B, C, D. So here on the right hand side I had B, here also I have B. So that means it is preserved. So this dependency is preserved. Then I have B goes to C. Again same thing, we find the closure of B on the G functional dependency set, and I find that only B is the attribute in the closure set. I cannot derive anything else. Why? Because if I so consider these two functional dependencies, A goes to BC and C goes to D, and with these two functional dependencies in your hand, if you have only B, you cannot derive anything other than B, right? Because on left hand side we have only A and C. I do not have B on the left hand side. So if on left hand side I do not have B, I cannot start anything from B. Correct? So since I cannot start anything from B, I will have only B as the value in the attribute set. So that means B has only B in the attribute set, but in this functional dependency, B was able to derive C. So basically in this functional dependency, B plus was B, C, D, yeah, B, C, D, right? But in this functional dependency, B plus is only B. So you see, this is the difference. In both of these sets, B plus is different, and that's why this functional dependency B goes to C is not preserved, it is lost, right? So that's why I say that G does not cover F. Okay, so this is the closure part is done, canonical cover part is done. Now we will go into functional dependency preservation. This is a little bit tricky thing. Not always. It might be simple, but might be sometimes it might be tricky. By the way, let us solve one question just for interesting purpose, because this kind of question might come. Okay. This is also, I think, it came in gate once. Okay. Very simple question, old concept. What are the candidate keys? I think this is kind of, if someone is interested, try it. Okay, try it now only. By the way, what is yeah, this is candidate key. Yeah, it's in week 5 only. Yeah. By the way, the table is ABCDEF. I think that is understandable, but anyways. So this is your table. Actually, this is very easy. I mean, from the first look, you should be able to find out. But anyways.
So, can I say, sir?
Yeah, go ahead.
A is the candidate key, BC is the candidate key, and DEF is the candidate key.
Correct. A is candidate key, BC is a candidate key, DEF is a candidate key. Why I gave this question is, it might be very easy in the first look, but if you go into solving it, it will take time. I mean, if you just take 1 second and look at it, you will understand that A, BC, and DEF are the candidate keys. But sometimes people try to, in the exam, they don't see the question, rather they just go into solving it by the normal rules, and then it might take some time. Fine. So now let's move to this new concept of dependency preservation. I hope lossless decomposition idea was clear. I mean, it was discussed. So what it means to be a lossless decomposition. So when I'm dividing a table into 2 subtables, I will check the common attribute between both of them. And if the common attribute between both of them, it can be one attribute, it can be multiple common attributes. So if the common attributes between both of them uh, basically determine any one of the tables, functionally determines all other attributes of any one of the tables, then we say that that decomposition is a lossless decomposition. So which is basically your criteria, your let's say R1 and R2 are 2 tables. So after you break them into 2 parts, so whatever is the intersection set between them, this can be intersection set can be one attribute, or it can be composite multiple attribute. So whatever is the intersection set, right? If that set functionally determines either R1 or R2, any one of them, right? And also I should not I should not lose any attribute, right? So R1 union R2 must also, I mean, basically equal to R. So this must hold. But if these 2 conditions are holding, then I say that the decomposition is lossless. So this I think was discussed earlier. I will now discuss the next part. So whenever you are breaking a table into smaller tables, there are 2 things that you have to keep in mind. The first is lossless decomposition, and that is the compulsory criteria. So while decomposing tables, By the way, why are we decomposing tables? We are decomposing tables because we want to reduce redundancy. And this is basically the starting point of normalization. In the next week, we will deal with more detailed way. So where we will follow different rules, and following those different rules, we will every time decompose the table. But whenever we decompose the table, the decomposition will happen in following the rule, this rule, I mean, these two rules. Okay. Sorry. Anyways, so while decomposing table, two things must be followed. The first part is lossless decomposition. The second part is dependency preservation. Now, this is a compulsory requirement. This is, I mean, desirable. So dependency preservation is not compulsory, it is desirable. If you can maintain that, it is good. But if it is lost also, then also it's not a big deal, but it is preferable to, I mean, desirable to keep the dependencies, break the table in such a way that the dependencies are preserved. Now, what we mean by that, we will come to that. But lossless decomposition is ultimately, it's very necessary, because if you do not do that, you are basically losing the record. You are manipulating the record. The record is getting changed. So that's why lossless decomposition is compulsory. Okay. So now coming to this lossless decomposition part. So what? Sorry, dependency preservation part. So let's say you have taken a table and you have broken it down into 2 or 3 tables, and now since we have broken it down into 3 or 4 tables, so let's take an example from here. Let's take an example from canonical cover is done. So let's take this example. What is this? R goes to AB goes to C. Okay, so let's take this one. Okay. So AB goes to C, B goes to F, D goes to I, J, A goes to D, E, F goes to G, H. So this is my FD set, and our table is basically R, A to J. First breaking D1 is, okay, we have many tables. First is A, B, C, A, D, E, D, F, F, G, H, T, I, J. So these many tables we have broken down our main table into. Okay, we have broken down the main table into these many tables. Okay, let's take only one example for the time being. We will come back to it later if required. So this is the thing. Okay. Fine. So now, since we have broken down our main R table into so many smaller tables A, B, C, A, D, E, D, F, F, G, H, D, I, J. These are the tables that we have broken. So this is, let's say, array R. This is, let's say, R1, R2, R3, R4, R5. 5 tables. Now, what is the meaning of dependency preservation? So the idea is whatever dependencies were there in the main table, right? Now, since we have broken it down into smaller tables, it might so happen that all the dependencies are not directly applicable. So let us see that. So AB goes to C. So if I apply this AB goes to C in this table ABC, will it hold? See, the data will be same. We are not losing the data, right? We are assuming the data lossless decomposition is done. So if lossless decomposition is done, the data will not be lost. If data is not lost, then these relations will be maintained. I mean, B goes to F, B goes to IJ. So all these relations will be maintained. The only problem is, since now we have decomposed the table, all the attributes in a particular functional dependency, considering a particular functional dependency, all the attributes present inside that functional dependency might not be together in any one of the table now, because we have now broken the table, and that's why the attributes got separated. Now, since the attributes got separated, the functional dependencies may be in such a way that the attributes present inside the functional dependency might not be together inside any one of the table. So you cannot apply that functional dependency directly. That's the idea. So what I mean by that is, let us see this AB goes to C. So AB goes to C. Is there any table where A, B, and C are together? So A, B, C are together in this R1. So AB goes to C is applicable over here. Someone wants to ask something? Go ahead, ask. No doubt? Okay. So AB goes to C is applicable over here. Next is B goes to M. So yeah, B goes to F is applicable over here. B goes to F is applicable over in R3. Just a second. Yeah, B goes to F is applicable over here. Now D goes to IJ. So D goes to IJ is applicable over here. Okay. A goes to DE. We have taken such an example, it is directly applicable, all of them. Bad luck. Anyways. So A goes to DE is applicable over here. So I thought that this is a complex one, but it's rather easy. So F goes to G. So likewise, in this example, it is not happening, but let us take another example. There you will see that all the functional dependencies are not properly applicable, right? So let us take one simple example which is there in the next discussion. Here, by the way, here you see that all the functional dependencies are directly applicable over in the smaller tables. So there is no trouble with it. So dependencies are anywhere preserved, right? You do not have to check for dependency preservation. Right? Whether it is lossless or not, I have not checked, but as of now, we are assuming it is lossless. Let us take another example. Okay, so in this example, let's say R A, B, C, D. Right? And our tables are, I have broken it down into AB table. R2 is BC table. R3 is CD table. So 3 tables, A, B, C, C, D. And let's say that functional dependency set in the main table was A goes to B, B goes to C, C goes to D, D goes to A. Right? This is a very common example, and again in the slides also you will find this, but let us see this. A goes to B, B goes to C, C goes to D, D goes to A. These are the 4 functional dependencies of the primary table. And now I have this decomposed table, right? 3 decomposed table. So now if I apply the same rules, A goes to B, let us apply. Yeah, so A goes to B is applicable over here. B goes to C, yeah, B goes to C is applicable over here. C goes to D, okay, done. D goes to A. Now tell me where can I apply D goes to A? So you see that we do not have D and A together in any one of the table, right? So since D and A are not together, I cannot apply D and A directly. and most probably then that means that D goes to A is lost, right? So you cannot apply it. By the way, so in the book Cork, DBMS Cork book, there are some errors in one of the algorithm. There are two ways of solving this dependency preservation, checking whether dependencies are preserved or not. In one of the algorithm there is, and that is the shortcut algorithm. The shortcut algorithm which is used, that is wrong in Cork. Okay, and Cork is one of the most famous DBMS book, so that is given wrong. So I would request you guys to follow what is being taught in as a part of our course. That should be fine. So particularly this example is given in a wrong way. Okay. So D goes to A is lost. So initially it seems so that D goes to A is lost, but it might so happen that D goes to A is really lost, or it might not be lost. What do we mean by that? We are not able to apply that dependency directly on any table because those attributes are not together. But still, I am saying that D goes to A might not be lost. So how is it possible? Right. So therefore you see that checking whether dependency is preserved or not is just not as simple task as simply allocating the dependency depending upon the attributes of the table and the attributes used in the functional dependency. It's not like that. I mean, mostly it is like that, but some corner cases will be there which will be difficult for you to judge. Okay. So we will follow 90% of the task is easy. Directly allocate the FDs in whichever table they are going. But for one or two dependency, you will not be able to do that. And for those dependency, the task that we will do is a little bit cumbersome. So there you will basically enumerate all the possible functional dependency that can be there. And then you try to find whether D goes to A is derivable or not. So what I mean by that, let us go step by step. So step one is allocating the functional dependencies that you already have, right? So A, B, B, C, C, D, they are easily allocated. Done. Now D goes to A, I could not allocate. So D goes to A is lost, I will not say lost, we will check for that. So how we will check for that? So the process of checking is, you will find the attribute set of all the attributes in each of the decomposed table, right? So let us do that. Sorry. Yeah. So these are the three tables, right? And now I will find the attribute set of all the attributes in these three tables. But let me just delete this CD and all those things. Discuss that. Now, what do we mean by finding the attribute set? This is very important. Please keep this thing in mind. When we are finding the attribute set, right? I told you I will find the attribute set of each attribute in each of these decomposed table. The functional dependency set that I will use to find this attribute set will be the parent functional dependency set and not the ones which are directly applicable. So I will not use A goes to B over here and B goes to C over here. Okay, that is done to actually figure out which functional dependencies are directly applicable. So don't say that I will use only A goes to B because AB is the only attribute, only functional dependency that is applicable on this R1. Okay, so it's not like that. So we will not do it like this. So that step one was just to allocate the ones which are directly applicable and find the one which is not directly applicable. So that is done. Then the step two is the one that what we are going to do now. So what we will do is find A plus B plus AB plus. So this is the reason I said it will be a cumbersome. So you see all the possible attribute set closure you have to find. B plus, but in most of the question it is simple, it will not be big, but in some question where, I mean, the situation, the question is complex, you have to do it in this manner, otherwise you will not find the correct result. In most question you don't have to solve it completely because you will anyway find the solution halfway. Right? Okay. So the thing is, I will apply on all these set of dependency. Okay. Don't forget this. Apply this check on the parent set of dependency. And not on the ones applicable. So now what is A closure? A closure from the parent set?
A, B, C, D.
A, B, C, D. Okay, fine. Correct. A, B, C, D.
Everything is ABC.
But I cannot write ABCD over here because in now here only I will apply the table constraint that since this table has only A and B, I will only write A and B. ABCD is fine. According to this, ABCD is only coming. But since in this table I have only AB, so I will write AB. Okay. So if you now you might say that if we are writing only AB, then we could have just followed this A goes to B dependency. So you will see the problem with that. Basically, this is the point where Corf is wrong. I mean, one of the algorithm of Corf is wrong. Right? So we will not follow these applicable dependencies. We will follow the parent one and you will see why. Just now. So here it is not happening, but now, just now it will happen. Wait. So fine. So at first I will apply on this one and I find ABCD is the set, but here only AB is there. So I will only write AB. Whatever is available, I will write that. Again, from B, what will I get? Again, ABCD, all of them, right? But I will only write A and B. What is AB? Again, A and B. Over here, what will I get? B and C.
Yes.
C and B. Okay, so now we have basically therefore completed all the attribute set by applying on this parent dependency. I'm telling again and again, apply on the parent dependency. Okay, so this is done. Now I need to check whether this DA is lost or not, right? That was the main task. So now we will use all these dependency that we have got over here, right? To derive D goes to A. So is D goes to A derivable from this? So let's say I call it F1 set. This is F2. If these Fs are basically the dependency set in each of the subtable. So if I say that F1 union F2 union F3, by doing this union, can I get T goes to A? Right? So let us see that. So starting from D goes to A means starting left hand side is D. So I can see that here I have so this means that here I have C goes to D, right? C goes to D and again D goes to C. These are the two dependencies over here. I mean, primarily that's the meaning. Over here I have B goes to C and again here C goes to B. C goes to B. Here I have A goes to B and here B goes to A. Right? So these are the three sets. Now let us check whether this is derivable or not. Right? So D is the left hand side. So F1 union F2 union F3. So 6 dependencies you have. Can you derive D goes to A from here? So D goes to C is there. Correct, right?
Yes.
C goes to B is there.
And B we have C.
D goes to A is there. So step 1, step 2, step 3. So from D to C, C to B, B to A. So therefore, the D plus on F1 union F2 union F3 is basically A, B, C, D. So since A is a part of it, therefore D goes to A is not lost. Although you cannot directly apply D goes to A on any one of the subtable, but in the data part, now what do we mean by that D goes to A is not lost? So in the table data, so when you have these tables, right? In the table you have this ABCD attributes, right? ABCD attributes you will have. Now this ABCD are broken down into subtable called, let's say, AB subtable. Then you have another table BC subtable, and then you have another table CD subtable. So that's what you have done. You have broken this thing down into 3 subtables. Now when I say that D goes to A is not lost, that means Although I do not have D and A together in any table, that's why I cannot show that. But if I merge these three tables together again, then the resultant table which I will have, right, resultant table which I will have, in that resultant table again this dependency will exist. I mean, if you see the data in the resultant table, you can observe that all the D column fields determine or will have the same value in the A column fields. When you create the resultant table, in the resultant table you will be able to find that D goes to A is there. Okay, by inspecting the data, you can understand that D goes to A is still holding. But if this D goes to A would have been lost somehow, then after merging these three subtables, in the resultant final table, you will not be able to see that D goes to A result is holding any. Okay. So, right. So, what are the steps? I will recap once again. If you have to check for dependency preservation, break the table down into the subtables. I mean, so whatever subtables you have. Now, first step is apply the dependencies which are directly applicable. So A goes to B, B goes to C, C goes to D. These are the attributes which are directly matching with the table. So CD completely together is there in R3. So apply CD. Like so, likewise, you will find out all the attributes which are all the dependencies which are which can be directly put on any one of the subtable. So that is anyway preserved. So that is done. If there is such a dependency which is not directly applicable in one of the tables, then the question arises what to do with it, right? So the way to check that whether it is preserved or not is to find attribute set closure of all the possible combinations of attribute in each table. And it might seem a little bit difficult task to do when you have larger tables, but it will be easy. We will do one more example and you will see that it will be very fast when we move through it. So we will find the attribute set closure of all the possible attributes in each of the table. The most important, in fact, the most important point of this whole process is while finding this attribute set closure, always apply on the parent functional dependency. Do not apply it on the partially applied dependency. So let's say you apply CD, as I told you, you have CD over here, BC, B goes to C over here, C goes to D over here, A goes to B over here. And now you see, okay, I will only apply on this functional dependency which I got. No, don't do that. Find this set on the parent functional dependency. Okay? But while writing the value, you don't have to write A, B, C, D over here because CD is not there in the table. So that is allowed. That is okay, right? So that you don't write, but apply it on the main table. Find it on the main table. Sorry, not table. I mean main dependency set. So once that is done, once that part is done, then what you do is basically convert it into functional dependency from these three sets that you got, convert it into FD, and do the union of these three dependency sets, right? And now by using this union set, check whether the dependency that was not directly applicable, right? D goes to A, which was not directly applicable on any subtable, check whether that can be derived by using the union of this dependency set. So if you can derive it, then that means that dependency is not lost. What is the meaning of that dependency is not lost? That means when you basically merge the three tables together or whatever X number of subtables together, you will again see in the resultant table the data is arranged in such a manner that the D attribute will have similar values similar values of A attribute whenever the D attribute was repeated, which is basically D determines a functional dependency's meaning, right? So that will be holding. So that means D goes to A is not lost. Okay, so this is derivable actually. Am I able to derive D goes to A using this union set? And this is actually plus. So tell me if you have any doubt in the basic process of this thing, right?
Sir, in this example, if there would have been a table ABC, then we would have taken 7 possibilities for that closure.
That's I will show it in the next example. Yeah, that is the trouble. Anyone else has any doubt? So let us take one more example and try to solve it. Yeah, so take this one. So the table is ABCD, which is broken down into two tables. Or 2 BCD. Okay, and the functional dependency set, initial functional dependency set was okay. So this is the. Now I have to check whether the decomposition is lossless. First is check losslessness. So is it lossless or not? So how do we check lossless? We will find the. You
Common
want to
set.
check? Go ahead.
So we will find the common set of attributes, whether it is present or not, and you can see over here it is non-empty.
So what happens in this case? Tell me.
So D is the common attribute over here.
Okay, so R1 intersection R2 is D.
And D is the key in R1.
And T determines A functional dependencies over here. So which is essentially that is nothing but R1 intersection R2 determines AT, which is R1.
R1.
Right. So this condition is here holding. That's why is it lossless? Yes. Now let's do the next check, which is dependency preservation. Now let us try to do that. So how to go about it? So first we will directly apply the dependencies, right? So I have the two table AD and BCD. So which are the dependencies that are directly applicable? So let us write it like this: AD R1 R2 okay. So inside R1 I can apply whichever. What are the dependencies that I can apply inside R1 directly? D goes to A, right? Anything else? No. Right? I cannot write anything else because even if I try to write AB goes to C or AB goes to D, A and B are not together. So I cannot write. So you can say that I could have written since A and B goes to C, D is there. So I could have written something like this in R1, but that is not possible again because here B is there. So I cannot write it. Okay. So D goes to A is the only dependency on R1 that is applicable. And over here, what can I apply?
Declosure.
No, closure is fine, but is there any dependency that I can directly apply in R2?
No, sir.
No. And as of now, I am not able to directly apply any dependency. So I am left over with this AB goes to CD1. So the under trial dependency will be this AB goes to CD. Is it lost? Since this is not directly applicable, therefore I have to check. Now we know the rule. How to check it? I have this AD table, so first I will find A plus, okay, D plus, AD plus. Here what we will do now, this will be tricky. We will find one by one. Let us do this first. So A will be what?
A.
Again, I will apply on this primary set. So A will be A. D will be
D.
AD. Why? Because using D you can go to A, right? AD. Now over here, coming over here, let us find D first. Okay, I'm not writing that symbol arrow now. So B plus, what will be B plus? On the
B.
only B. What is C plus?
C only.
Only C. What is D plus?
D. A.
Okay, so
Only
D
we
is
have to
there.
remove A.
Yeah, so let us do D and A is there, but now I cannot. Yeah, so D and A will be there, but I cannot find anything else. But since A is not there as a part of R2, it doesn't matter. I will only D. So basically, therefore, it doesn't make any sense. These are trivial dependencies. So I will not write the trivial ones now for ease of. So since these are one attributed, B determines B doesn't make any sense. So we will delete all these single ones. Here also it was A determines A. So it doesn't make any sense. So yeah, this is also AD determines. Obviously, AD will be determining itself trivially. This one I will not remove because D is determining a new non-trivial value A. So let us keep it. Okay, so BCD is done. After that, what we will do pairwise. What is BC?
BC only.
BC. Yeah.
Trivial again.
So B and C, both of them were there again trivially. So I will not write from now the trivial ones. Okay, just keep that thing in mind. BC is there. Then what is CD? So CD will be what?
CD again. Because we
No.
can remove A.
A is not there. Correct. A is not there. So nothing else. I will not write CD. So finally there is BD. Third pair is BD.
Again BD only because we have to remove A.
Yeah. So if I write BD over here, then basically we will have B, D, and A, but A is not there in the primary set. Right? I mean in the table. Sorry, in the table A is not there, so I will not write. So again BD. So all these two pairs are gone. What's left is now 3 pair. Right? We considered all the two BC, CD, and BD. Right? 3 pairs. Now 3 altogether BCD is there, but then anyway it will have BCD itself. Right? BCD will be BCD. So then also it is again trivial. So all of the functional dependency on R2 are basically trivial. And only functional dependency that I have in R1, and that is D goes to A. So this is the only functional dependency that I have. So now if I do that, so I mean you can see that if I use this F1 union F2, F2 is basically full of trivial dependencies, right? B goes to B goes to B, C goes to C, D goes to D. I mean, it doesn't make any sense. So F2 is basically whole set is trivial. We have seen that. It's trivial. And F1 has only one dependency, meaningful dependency, that is D goes to A. So using these two union, using the union of these two, can I derive this AB goes to CD? Never. I cannot derive that. So this means since I cannot, so this is not possible. So since I cannot derive this, only I have D goes to A. So that means this dependency is getting lost. Got the point? So you see, if I break, so this is lossless, yeah. So the dependency, sorry, the breaking down of the table was lossless. We saw that, right? It was lossless over here. We see, but is it dependency preserving? No. So is it lost? Yes. Now tell me, any doubt? Okay, so do you want me to solve one other example, or did you guys understand?
So please take one more example.
Okay. Will it be something new? B, E, C, D, E. Supposed to be good to there. This is something I hope will be okay. Yeah. So the table is A, B, C, D, E. The FD set is E. Yeah, this was there in one of the gate sample paper, I think. Okay, so the broken down relations are what? R1 is ABCD, and I am writing it here only. R2 is DE. Yeah. Fine. So these are the two tables. This is the dependency set, right? So we will proceed accordingly. First step is directly apply the ones which are applicable. So A goes to BC. Okay, A goes to BC is applicable on R1. So let me write here R1. So A goes to BC is applicable on R1. C goes to DE. C goes to D and C goes to E. Basically, there are two dependencies if I break it down. So let us keep it like this. C goes to D, C goes to E. Two dependencies are there, right? So if C goes to D, one, so let us write it in this way. So this is broken down into C goes to D, comma, C goes to E. Okay, now C goes to D is applicable on R1. So I'm writing R1 on top, but C goes to E is not applicable on R1, right? Okay. D goes to E is applicable on R2. So only one dependency C goes to E is under consideration, right? So we will check that if C determines E is lost. So as a part of this decomposition, or due to the reason of this decomposition, is C determines C lost or not? Now let us repeat the same steps. First is what? ABCD is there. I will find the closure. Right. Just 1 second. So if I do it in this manner. Anyways, chalo. So again, so we will be a little bit fast now. So what is ABCD is there. So ABC. Yeah, ABCD, right? ABCD.
Yes, sir. E is part of other table.
So A is ABCD. B is what?
B.
B. C is what?
CD.
C is CD. And E, oh yeah, so D is what? E is other part, so only D. So I will not write B and D. What else is there? So let us find out AB together. So what is AB?
So whenever A will come, we'll always get AB first.
Will come, correct. So this is the observation. That's why we will not write anything A, B or like that. So other than A, we will compare the other patterns. I mean other pairs. So forget A. What will be B, C?
BCD.
BC will be B, C, D. Acha. So BC is done. BD.
BD only.
BD is BD.
Yes,
BD is
trivial.
BD. BD is BD. So I will not write.
CD is again CD. Trivial.
CD is again CD. Yeah. CD is again CD. Just a second. C, D, E, 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 E. Okay. Only this is there. Yeah. Okay. So this is done. Okay. So so two pairing done. DC we have done. CD we have done. BD we have done. And now only three pairing is there. Again, I will not consider A because anyway A will hold all of them. So three pairing, only one is left other than A. That will be BCD.
Yes, sir. So it's trivial again.
BCD is trivial again. BCD is again. BCD is trivial again. Correct. So I will not write. These are the dependencies that I got. Now in R2, let us see what I get. So what is D? Will be DE. What is E?
Trivial.
Only E, trivial. And if I consider D and E together, then also that will be D and E only. Right? Okay. So I got these two sets. So what are the dependencies I get over here? So A goes to sorry. A goes to basically all of them, B, C, D. BC goes to or CV, whatever. CV goes to D. And C goes to again. So this is, if I say C goes to D, that this C goes to D and BC goes to D are basically redundancy is coming, right? Because C itself can determine D. But let us don't complicate things. Let us keep it like this only. So CV, C itself goes to D and CV is also going to D. So that means B is not required actually. That's the point. But let us not go into that part. Let us keep it like this. Because our main motive is not to reduce. We are not finding canonical cover. We are basically finding whether dependency is preserved or not. So these are the dependencies. Now what are the dependencies over here? D goes to E. So these are the two sets of. So what is this? This set is F2. This set is F1. Now what we will try to do is
We were finding C, determine C or not.
correct. So F1 union F2 plus whether it derives CE. So is it deriving? So let us start from C. I have C goes to D
Yes,
and
sir.
D goes to E.
Yes, sir.
So starting from C, I have C goes to D, then D goes to E. This is from F1. This is from F2. So we have C goes to E. Right? So is it derivable? Yes, it is derivable. So is the dependency preserved? Yeah, the dependency is preserved. So although it seemed like this was lost, but no, preserved. Fine. So we have solved some questions of dependency preservation. Lossless part is already done. Canonical cover we did. That is important. Yeah. So that was it. I don't think there is anything left this week. Right? Any doubt?
Why are you not written that AB closure set in the R1 relation?
Maybe closer set means? That is trivial, na? What will be AB closer set? Let us see. The trivial one I did not write. What will be AB set? A, B, then C, D. Right? So anywhere where A is there, it is by default ABCD is coming. So I don't have to write. That's why I have not written AC. I have not written AD. So once I have seen that A is determining all the values ABCD, I have not written anything where A is there. Like AB I have not written, AC I have not written, AD I have not written, ABC I have not written, ABD I have not written, ACD I have not written. Right? All those things we have eliminated. Why? Because A has itself found all the values, all the 4 values in the table ABCD. So therefore, this is just all of them will anyway ABCD, ABCD. So all of this will be ABCD. Right? All of them will be ABCD because I don't have to see the other attribute. A itself will find ABCD because A on its own is determining ABCD or defining ABCD. So that means whatever A I add C, I add D, I add A, B, C with A, I add B, D with A, doesn't matter. A itself will determine all the variables. All the attributes. So therefore we have ignored those.
Okay, understand.
I mean, I will not get any new information, right? So we are trying to keep things simple. I mean, if I don't get any new non-trivial dependency, then I will avoid it. In fact, this is also trivial. CV goes to D and C goes to D is also trivial because if C goes to D, then CV goes to D is not required. This is also trivial. So C goes to D is the only dependency that you need. A goes to BCD, C goes to D, and D goes to E in F2. These are the 3 dependencies that you need to judge that all the dependencies are preserved. Okay, fine. So, any doubt? No one has doubt? Fine. So, I will end today's session now.
Sir, in the last example, we could see that, in some example, we could see that there are decomposition wherein we have 3 or more attributes. Do we expect this kind of question in the exam because it is going to be lengthy?
How much time? I explained it and I also solved it. It took 3 minutes. If you are practicing it, no matter. So see, what was the trick over here? If you tried to find A, B, A, C, A, B, D, then it would take you time. But we have to have this observation that if I am taking A and this ABCD is already defined by A, then I will not go and try to find any composition with A. I will not go and find AB. I will not go and find ABC. I will not find ACD. I will not find AD. I will not ignore all of them. So you can actually get time by having these beautiful, intelligent observations, right? So that's what will come with practice. So you will see and observe that these are the things that I have got, and I can eliminate the enumeration one by one. So yeah, questions will come, but nothing unexpected will happen. If you have practiced well, you will get the answers.
Okay.
Okay, thank you everyone. That was it for today's session.
Thank you, sir.
Thank you, sir.
Thank you.